Wow. This is the first time in my career that I've ever come in during March break before. I mean, it's called a break for a reason. I should be in Disneyland right now. But not gonna lie, I mean, the school is nice and quiet and cozy, and there's no regular hustle and bustle of the school day. So it's nice. I mean, I could go for a coffee, that'd be great. But thank you for investing your time into your own academic careers by watching this video. And it's going to be a long video, so that's just a warning to you because it's the intro of planes. Okay, so let's get into it. Lesson 4.1 is on the vector equation of a plane, and it looks pretty much the same as the vector equation of a line, but just a little bit longer. So let me show you how we create it. On the left-hand side, you'll see a diagram of a plane with 3 points. And so a plane is a two-dimensional flat surface that we can then write in a three-dimensional space. Okay, now what we really need in order to create this equation is what I've written in blue and green on the right-hand side. If the teacher on a test gives you 1 point and two direction vectors that are non-collinear, that's actually all you need in order to create your equation. But rarely are things so easy, right? So they might instead give you on the left-hand side 3 points instead. And so I'm going to show you how to find the equation just from those 3 points. Technically, there are infinite number of points that are lying on this plane. And each of them, if they were in, say, 3 dimensions, would have their own unique position vector, right? So what you do is you grab 3 of them. I'm just going to color coordinate with the right-hand side. So the blue will be my 1 point on a plane. And I can choose 2 other points that I can then create 2 green non-collinear direction vectors. So we'll call this one AB. And we can easily find it because we have all 3 points. So we can take OB minus OA in order to find the vector AB. You could do the same thing for AC. Okay, in fact, any vector that is a direction vector on the plane can then be put tail to tail with each other and be our 2 direction vectors. So I can always take this one, move it over here, tail to tail, and just have the point in between, and there you go. As long as those 3 things, your 2 direction vectors and your point, all lie on the same plane, you can then describe any of these position vectors for random points. Okay, so let's get into the second diagram. Now you see it in a 3D space, and I'm now going to call a PO instead. So I'm going to call it P naught as our original point, and my 2 direction vectors, I think I'm going to use 1 letter instead because I'm lazy. Okay, so A and B. Now, how do we actually create the equation? Well, probably should have written this again before instead of writing it twice, but that's okay. In my third diagram, what I have are the same things that I had in my second diagram. But let's just say that the random point that I wanted to find the position vector of is, I don't know, over here. We'll call that P. My goal is to find the vector equation for this, which is OP. Okay, now P could have been anywhere on that plane, and so we're trying to find a general equation that describes any position vector for any point on the plane. And we do that by extending your A, so some scalar multiple of your vector A, plus, I'm going to write B here instead because that's an equivalent vector, but it's a scalar of B. And notice that my scalars, I'll also call it my parameters. Those scalars are different letters because we don't know that S was extended the same length as T was extended. Or rather, we don't know that A was extended the same amount as B was extended, so S and T are not the same. Okay, so what we're going to do is we're going to say, okay, SA plus TB is my resultant from my P naught to my P. And that's what this equation right over here says. I can write P naught P is equal to SA plus TB. Okay, now if I decided to change this instead to a subtraction, a vector subtraction of position vectors, I would have OP minus OP naught is equal to, and then all the rest. Now to make things even more complicated, or I guess less complicated because we can rewrite this in one letter instead, why don't we just change those to r's? Okay, so I have this, and now just rearranging my equation, I'm going to move that to the other side, and it becomes a positive. This right here is the equation for any position vector for any point on the plane. Because this guy right here, your r, is also written like this. Okay, which could be a point or it could be a position vector, whichever one. Notice that we do write that s and t at the very end belong to all real numbers because they can be anything, and we're going to use s and a different letter t because we don't know that they're going to be the same scalar multiple. Okay, so showing you guys the vector equation and the parametric equations, they look like this. So here you have your r, which again can be written as x, y, and z, is equal to p naught plus your s parameter, which is a scalar, multiplied by your first direction vector, plus your second parameter multiplied by your second direction vector. And s and t can belong to all real numbers. That is slightly different than how we had written the vector equation of a line. So notice that you have, this one has two direction vectors and two parameters, whereas the line only has one. And at the end, you can also solve for any of your individual components of your points. So x is equal to x naught plus s times your x component, that's what I'm trying to say, x component of your direction vector plus t times your second x component of your second direction vector. Holy cow, that's like a mouthful. Okay, so you can also solve for your y and your z separately as well. Okay, let's get into some examples. All right, example number 1. What is that pi 1 thing? Okay, so let's explain. When you have a line, we call it line 1. When we did intersections of a line, we had line 2. Well, when we have planes, I don't know why, but they decided to call it pi 1 to indicate that it's a plane. And then the second one, I'm just going to draw something that's not parallel. This one we'll call pi 2. Okay, so all we're saying is we're going to start looking for pi 1, and that's why we have two dots and not equal signs, because you're already going to have an equal sign in your equation. So let's take a look at what example number 1 is asking for. A, the vector equation of a plane through a point with direction vectors A and B. Oh, great. Okay, so they gave us everything that we need. They're like, hey, give me the point. All right, no problem. Okay, two direction vectors. Okay, no problem. Put your two parameters in front of both of the direction vectors and add them all together. There you go. Bada bing, bada boom. You're done. Okay? All right, so now B. B is asking, remember how there are like infinite number of points all along your plane? Well, from this plane specifically, which describes this guy, I want to know if you can tell me 3 points that belong on that plane. And that's actually very easy. All you do is you decide whatever number you want to place into S and T, and that will lead you to a point on the plane. Okay, so as you can imagine, there would be infinite number of answers, and so guys, don't be annoying and like pick really weird numbers like 59, okay, or like 67 or 103. Just pick nice numbers like 0 and 1. It'll make your life easier and make my life easier. Okay, so plugging them in, I put my 0 and my 1, so again, you're choosing whatever two numbers you want, into your S and your T, and then solving. So 0 times this entire vector is going to give you a 0 vector. So it eliminates everything, or it makes it really unnecessary to include in the answer. Okay, your 1, you're going to multiply your scalar in, which doesn't change anything. That's why I chose a 1. It's very easy. You could have chose a negative 1 too if you really want to. And then you're going to add each of the components together. So this is my x, and this is my x, and you're going to get your new x. This is your y, this is your y, get your new y, and so on. Okay, so that's 1 point on the plane, or 1 position vector, I should say, on the plane. You can choose new numbers, and just do it again and find two other points that lie on this plane. So those two questions are fairly straightforward. When I get into the second question, because I can count, it gets a lot more difficult. So not a lot more difficult, I should say it gets longer. So I'm sorry, this question is going to be quite long. Determine the vector and parametric equations of a plane through 3 points. Okay, so like I said, we can get questions that don't give us exactly what we want, and we might just have to find them. Okay, so we have a point, which I'm going to put in this color, and we have two other points that I don't really know what to do with other than, okay, so that orange point, easy. I can put that into my direction vector, my vector equation right away. I could have also chosen A or B to put into my vector equation. It really doesn't matter. And so you can kind of see that you'll get multiple answers that are all correct. Now what I have to do is I have to find my direction vectors. So these are not direction vectors, they're points. So you have to create direction vectors. And what I did was I decided I'm just going to take P and A, do a vector subtraction, and get a direction vector. You could have took like A and P, it really doesn't matter. As long as you're just combining two of them in any direction, you have two direction vectors. Okay, so let me grab my colors. I created two new vectors, and I'm just going to call it little a, because it's easier, and little b right here. Notice that in B, I actually didn't stop here, and I'm going to explain why. You can stop there if you want to, but notice that you have a lot of negatives. If you ever have negatives, or you have, say, like larger numbers that you can reduce the entire vector by, you can definitely do that. So I pulled out a -1 as my common factor, and I just left like a really nice direction vector with smaller numbers and less negatives. And it's your choice. You can do this. In fact, I think normally people would prefer to do something like that. The other way is not, like, this guy is not wrong to use. It's just more messy. So that -1 doesn't disappear. It actually gets absorbed into your t. And so you're left with your direction vector as nice small numbers, and the -1 just disappears into your t. Okay, because you know that t can belong to anything, so we're just going to sweep it under the rug. Your other direction vector you're going to place right there. And the note right before basically just says you want to make sure that these are non-collinear. And so if they're not scalar multiples of each other, you know that they're actually non-collinear. Okay, so it's just like a little check you want to make. Okay, so we're done our vector equation. That's done, yay. And now we're going to do our parametric equations, which I'm going to do in a different orange. Okay, so that's these guys down here, where we're going to take your x, y, and z components and figure out what they are equal to separately. Okay, so x is equal to this x plus this x plus this x. Okay, so that's going to be the 0, you don't have to write. X is equal to s plus 2t. And your y is equal to -1 plus 2s minus 3t, which you have right there. Okay, so you can do the z on your own. Make sure that you're saying that s and t belong to all real numbers again. And remember this parametric equation, because I'm going to be using it in different slides. And so I'm going to be referring back to it, and I don't want you to get confused. Okay, so I'm going to move on to B. Does the point lie on this plane? So by this plane, they actually mean the one that I had in parametrics in the previous slide. So I'm going to do that in orange right here. And what they're asking you is, does your point lie like somewhere else, or is it actually on the plane itself? And what we do is a simple substitution. If you can substitute the point onto the equation of the plane and everything works, then that means that it's lying on the plane. If you substitute it into the equation of the plane and something just doesn't seem right, then it's not. Okay, so let's check it out. You have your x, y, and z, of your point that I'm then going to write into, using orange, the parametrics, whoops, of each of those components of my last plane, minus 3t, z equals 2 minus 3s plus t. So I'm going to substitute into my x, y, and z, and notice that I still have s's and t's. Like, you don't have 3 variables now, you now only have 2, which is great because we know how to solve for 2. You just do substitution and elimination. Let's start solving for the parameters, and we're going to start looking for if there are any inconsistencies. Okay, so we'll call this equation number 1, equation number 2, equation number 3. And I decided to use, you can use whichever 2 you want, so I used 2 and I tripled equation number 3. And I did elimination. When I substituted, I made sure that I was still using one of the 2 equations that I had originally used, so equation number 2 or equation number 3. I left equation number 1 alone because I wanted that as an unbiased source, just in case I made a mistake somewhere. So once you have your S and your T, you're going to do a check with your unbiased source. After I did my check, I noticed that my left side and right side weren't really consistent. And so since they weren't, it really did give me an indication that that point was actually not on the plane and was floating somewhere around it. Okay, so this last question is a lengthy one. And it takes like a little bit of like understanding and visualization. So I'm going to try to show you this and then we'll do the math behind it. I'm going to pretend that line 1 is purple. Okay, and we'll just draw it maybe somewhere here. Okay, so this will be line 1. And then we also have our plane, which I gave you the equation for again, just to remind you, that is the vector equation that we found on a previous slide. Okay, so that's going to be that guy. Now, on the left-hand side, I wrote down the line 1 in parametrics because it's just easier to see the point, the position vector for a point, and the direction vector. Okay, so what you can see is there's a 0 plus right there, and so the 6, the 1, and the 0 are my position vector for the line, and then anything in front of a U is my direction vector for that line. Okay, so you have a point and then you also have a certain direction. All right, now what I'm trying to figure out is that line on the plane? Like, is it drawn something like this? Or is it not on the plane, but does it actually pierce through the plane itself? If you think about this logically, you'll know that this one is parallel to the plane. This one is actually also parallel to the plane itself. Okay, now this guy, because it's piercing through and intersecting, it is not parallel. Okay, so sorry, that's that one right there. If I distinguish between the 2 on the right-hand side, this one is actually parallel and distinct, whereas this one is parallel and coincident because they have infinite number of points of intersection, whereas the one above has no points of intersection, right? So how do we actually show that we're talking about the line that is parallel and coincident? Does it lie on the plane versus is it parallel and distinct? Well, first of all, what I could do is I could just eliminate this guy altogether. I want to eliminate that case by saying, oh, do they actually have parallel slopes? Why am I saying slopes? Direction vectors. Sorry, direction vectors. If they're not parallel, then I can eliminate that one that pierces through, and I'll be left with the 2 cases on the right. Now, in order to distinguish between the 2 cases on the right, what I could do is choose a point that is on the line and see if it's actually also on the plane, because if it is, it's this guy. If the point is only on the line and not on the plane, it is this guy. Okay, so that was like 2 separate things I had to do. Number 1, I have to see if they're parallel. And then number 2, I have to check out if a point is actually on the plane. And so let's do that. That's a lot of work. Let's just do that separately. So on the bottom, you'll see a box that says, the first thing I want to do is check if they're actually parallel to each other. And that is called coplanar. So if the direction vector is coplanar to the two direction vectors that are on the plane, then we can actually say they're parallel. If they're not coplanar, then they're not parallel. Okay, so what we have to do is see if the direction vector, which is this guy, can be written in terms of your A and your B, like scalar multiples. That will tell me if it's parallel or not. Okay, so here we go. We're going to say, can my direction vector, which is part of my line, be written as a combination of your A and your B? Okay, because if it can, it means they're coplanar and they lie on the same plane, which means that they're, it lies on the same plane, but it could be above the plane. Geez, I don't know if I explained that very well. It just means that they're parallel to each other. Okay, so what I did was I made my purple equal to a scalar multiple of both my orange direction vectors. I wrote them again here just in case you don't remember them. So this one was the pink and this one was the blue. And then I just started to solve. Okay, so I have my x component, which is this, is equal to m plus 1n. Well, why did I do that from the plus sign? I don't know. Plus 2n's, and that'll give me equation number 1. I'll do the y's to give me equation number 2, and the z's to give me equation number 3. And as you can imagine, substitution and elimination, I'm going to start checking for my m and n's. Okay, and I'm just going to scroll down a little bit. So what I decided to do was, I think it looks like I doubled equation number 1, but I kept equation number 2, and I did substitution and elimination, making sure that I substituted back into equation 1 or 2, but I kept 3 unbiased to do the check. Since the check works out, it means that I can actually write the direction vector in terms of A and B, just like this. All right, which means that it's coplanar, and that means that they're parallel. Okay, so in that case, we don't have a line that pierces through the plane. We actually have one that either the line lies above parallel or it lies on the plane parallel. And so we have to do that check now if the point is actually just on the line or if it actually lies on the plane. Then we can distinguish whether it is distinct or coincident. Okay, so that's what the box is basically saying. I'm going to take a point from the purple line and I'm going to put it into the orange plane. So I have all of this, pi 2, which is my plane, and the 2 just distinguishes from line 1. We're going to talk about plane 2. Okay, and we have the vector equation and the parametric equation, and I'm going to substitute, because the parametric equation is so much easier, my x, y, and z into the parametrics of my plane. Okay, so that's what you get right down here in this step. And then again, lots of substitution and elimination. Okay, so I get equation number 1, 2, and 3. Did substitution with a couple of them, and then decided to do my check with the unbiased equation. So looking at the check, it looks like the left side and right side are not the same, which means that that point is not on the plane, and that means that they're actually not coincident. The line is lying above the plane, but it's parallel to that flat surface. So it's going to be called parallel and distinct. All right, if you have enough energy, let's go through 2 more, and they're actually pretty easy. Example number 3. Determine the vector equation of the plane through the point and is parallel to another plane. Okay, when it's saying that it's parallel, let's just draw this so that you can kind of see. Let's say that, here, we'll use the same colors that I always use. Here's one plane, and you're saying that this one is going to be first one, pi 1. We're going to see if it's actually parallel to another plane, which is this guy right here. Now, pi 1, which is your first plane, has all of these equations. Okay, and so what we're doing is we can actually see some of the direction vectors that are on pi 1. Okay, and I've written them right here because all you're looking for are the coefficients in front of your s's and your coefficients in front of your t's to distinguish the differences between like your a vector and your b vector, your two direction vectors. So let me see if I can just write out the s's. There's a 1 in front of the s, the 1 in front of the s, and the 1 in front of this s, and that makes this guy. Then you have the 3 in front of the t, the -1 in front of the t, and the 1 in front of your t, so that gives you that other direction vector. And those will give you, here's your B, there's your A, okay, are your two direction vectors on that plane. Okay, so what you want to do now is you want to figure out the new equation of the orange plane. It has to have the same two direction vectors because it's parallel, but you also want to make it so that it goes through that one point, and that point is this guy right here. Okay, so what you're going to do is you're just going to write the same direction vectors with your scalar multiples, so your parameters, and then write down that last point right here, and that is going to be in orange your pi 2. And finally, the last one is pretty much asking you the same thing. Determine the parametric equations of a plane parallel to the xy plane, and they're going to give you a point that they want it through. So already you know that your point is going to go right here. The only problem is your direction vectors. Okay, so if I decide to draw this, you have, and I'm sorry if this is really messy. Okay, that's your z, this is your y, and your x. So if we're talking about the xy plane, we're actually talking about, and I'm going to do this in purple, I want this, which is, why don't we just use like your basis vectors? Because this is going to create a plane that is only on your x and y. All right, so we'll call this plane number 1, your xy plane. So I have each of those direction vectors that I'm going to base off of the basis vectors for x and y. Now what you're saying is you want to create a new vector that is parallel to that one. So how do I draw this? Like somewhere up here, parallel, this is going to be pi 2, has the same direction vectors, so your I and your J, but it also has to go through a specific point. And so that point is this guy right here. Well, your I and your J, which gives rise to your two direction vectors, your A and your B, we're going to put those right there, substitute the point in, and there you go. That's your vector equation with your S and your T parameters. Then we're just going to rewrite it as your parametric equation, which I'm going to leave for you because this is a long freaking video. Okay, so have a great day. Enjoy wherever you are right now, and please ask questions if you have any issues. Okay, have a great day, guys.